so far with respect to Fourier series coefficients. We have been talking about how to find a sub k. Those are our Fourier series coefficients. How do we find that given a periodic signal x of t? So if you have a periodic signal x of t, how do you find its Fourier series coefficients? Well, you simply use the definition integral x of t e to the minus j k omega naught t dt, where omega naught is your fundamental radian frequency, capital T is the time period, and you're integrating over one time period. X of t is the periodic time domain waveform x of t. And k is referring to the index, right? So when k is 0, that's the DC component a sub 0. When k is 1 and minus 1, those are the fundamental harmonics. And then you have the second harmonic, magnitude of the second harmonic, and so on. We also noted that a sub k, is a complex entity. So it could be, it will have some phase, it will have a magnitude and it will have a phase. And then we started looking at the pulse train, right? The pulse train, which we defined as T1 comma T. Let me take a look at that definition right here quickly. Let's see. We said pulse train T1 was the time period for which the signal was on. This was centered around 0. And let's see, you had something like that, and that goes here, and T1 is right there, negative T1 is right here. This was the pulse train, T1 comma T, why T? Because if this is 0, then that is T. So it's periodic with a time period T, and it is on for between negative T1 and T1. It is centered around 0. So if that is the pulse train, defined as pulse train, inside the parentheses you have T1 comma T, then the Fourier series coefficients a sub k, this is time by the way, and this is the pulse train, a sub k, we derived these as 2T1 divided by T sinc k omega naught T1 for all k. So that was the reference result that you guys are going to be referring to many times. I posted a Fourier series and Fourier transform tables document under general resources on the Piazza site. Please take a look at that. It has a lot of the properties of Fourier series that we will be going over today. Those are all listed in one document. So please refer to that document as you go through problems on Fourier series. All right, so that's a reference result. We are going to be needing that today at some point, many times. All right, let's keep moving here. Now we are going to get into Fourier series coefficients of impulse train. What is impulse train? Well, you have one impulse, and if you have a train of impulses, then that would be an impulse train. So that's what we are going to do first. We'll try to find out the Fourier series coefficients of an impulse train. Then we will take a look at the fundamental period of sum of periodic signals. So if you have a sum of periodic signals, each of those periodic signals could be sinusoids, for example, and if they have different time periods, how do you find out the time period of the sum of those periodic signals? So we'll tackle that next. Then we will get into the core of Fourier series coefficients discussion. Properties of Fourier series. How about linearity? How about a vertical shift in the signal x of t? What happens to the Fourier series coefficients? What happens when your x of t, it gets horizontally shifted, which means there's a time shift. It could be a delay, it could be an advance. What happens to the Fourier series coefficients when you do this in the time domain? What happens when you do a time flip on x of t? What happens when you differentiate x of t? And there are a few more properties that we will get to beyond this as well. Now, the first thing that I want to note before I go further is any change that you make in the time domain to the signal x of t, right? Anything that you change for x of t, there will be some corresponding change to the Fourier series coefficients. So if you move the signal up and down, changing the DC component, then a sub 0 will change, all the other Fourier series coefficients will not change. If you move it left and right with respect to a horizontal shift or a time shift, then the Fourier series coefficients will remain the same, but there will be a phase term that gets added on. When you differentiate a signal, there will be some corresponding operation that needs to happen in the Fourier series domain. So we'll take a look at. So I want you to think about this in this way. If I change some aspect of x of t in the time domain, then there will be some change in the Fourier series coefficients as well. So when you go about talking, when we go into the properties of Fourier series, we will be addressing that mapping. What I changed in x of t, what did it cause, what is the result in the Fourier series coefficients. All right, so let's begin with the first slide here, which is Fourier series existence. Well, I'm trying to find out a sub k, and it depends on x of t. So does x of t matter? Well, will the Fourier series coefficients exist for any and all periodic signals x of t? The answer is no. So the Fourier series existence depends on the energy in x of t. So if the energy in x of t is finite over a time period t, then that indicates that the Fourier series exists, and you can actually find out the Fourier series coefficients. So if the periodic signal x of t with time period cap t satisfies this relationship, which is you're trying to integrate over one time period, you're trying to find out the absolute squared of x of t, which is essentially the energy of x of t, if that is less than infinity, which means energy in x of t over time period t is finite, then the Fourier series coefficients a sub k are finite, and the approximation error, which was the difference between representing x of t as is and representing x of t as a summation of Fourier series coefficients multiplied by an orthogonal set of functions comprised of the complex exponentials. So that approximation will go to 0 as k tends to infinity. So there is a condition on that Fourier series existence. Now, let's get into the Fourier series of impulse train. Sander asks a question, is this a necessary and sufficient condition? Yes. If the energy is finite, that means that it's a necessary as well as the sufficient condition. The Fourier series of impulse train. An impulse would have been just one thing, one impulse right in the middle, for example, or one impulse right here. But because it is a sequence of impulses that are going on from negative infinity to infinity, they are periodic. That is what makes it an impulse train. Like you had a pulse train, now you have an impulse train. What is the time period of this impulse train? 0 t. So the time period of this impulse train should be cap t. Consequently, omega naught should simply be 2 pi divided by t. And f0 should be t divided by 2 pi. Sorry. All right. Can I write x of t in a slightly different manner? Let us see. I can write x of t as a summation of impulses. Let me try to write that down. Summation. I'm going to use k as my index here. Maybe I can use something else. Maybe I can use n. I can scan n from negative infinity to infinity, where n is an integer here. And I can write x of t as a summation of impulses that are present at t minus n cap t. So as n scans from negative infinity to infinity, you get an impulse here, 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 here. When n is 0, you get the one in the middle. And then as n goes higher, you get t, 2t, 3t, and so on. N is an integer. So I can write x of t, the impulse train, as a summation of impulses that are present at 0, plus and minus t, plus and minus 2t, plus and minus 3t, and so on. All right. Now let's try to find a sub 0, the DC term. As we usually do with Fourier series coefficients, first try to find a sub 0. The formula to find a sub 0 is 1 over t integration over one time period x of t dt. How do I know that? Well, I just substituted k as 0 in the general equation, and I got that. So when I start substituting x of t here, so I need to only scan for one time period. So let us try to see which time period is going to be very helpful. So I will try to just look at the one in the middle here. I will scan over that one to find out my a sub 0. So what is that going to be? 1 over time period. Okay, 1 over time period is simply 1 over t. Then I try to scan over one time period. What time period should I choose? Should I choose 0 to t? Should I choose something else? We learned from earlier discussion that if the signal is even, then it is very helpful to choose a time period in a symmetric manner. So minus t over 2 to t over 2. All right. Then I have x of t, which is what? Delta of t. There is only one impulse there, dt. If I integrate over that impulse, I get a 1. So I got 1 over t multiplied by 1. 1 over t. So t says, I think f0 is either 1 over t or omega over 2 pi. Well, if I write it, so here, this is what I think I'm going to explain here. So if the time period is t, then the fundamental frequency will be 1 over t, right? And this will also be, but what about omega naught? Omega naught will be 2 pi f0, right? Which means it will be 2 pi divided by t. Do you write 2 pi divided by t for omega naught? Yes. And f0, right, f0 is 1 over t, and 2 pi divided by omega naught. Yes. Thank you, T. All right, let me erase this off. Let's go to the general case. Now I need to find the Fourier series coefficients a sub k, the general case. Let us do that. 1 over t. I have negative t over 2 to t over 2. What is x of t? Delta of t. E to the minus j k omega naught t remains as is, dt remains as is. What will this be? When you multiply a function of time with an impulse that is also a function of time, then you need to evaluate the function at the time at which the impulse is active. The impulse is active at time 0, which means I need to evaluate this function at time 0. So let's try to do that. Equals 1 over t integration negative t over 2 to t over 2 remains as is. Then I have delta of t that remains as is. Then I need to evaluate e j k omega naught 0 dt. What do I have here? This is going back to a sub 0, which means this will evaluate to 1 over t again. That's it. So I have a sub k as 1 over t in the general case as well as for a sub 0. So this, I can use this to sketch my Fourier series coefficients here. So let me sketch them right here. So I've got k on my x-axis and I've got a sub k on my y-axis. When k is 0, say we are right in the middle, so that's 0. I got a sub 0 as 1 over t. So let's say we have sure that guy, and the height of that guy is going to be what, 1 over t. Now how about when we go for k equals 1, 2, 3 and so on. So let's say I have 1 here, 2 here, 3 here and so on, and I have negative 1 here, negative 2 here, negative 3 here and so on. What is going to happen there? Well, simply this is going to get repeated. 1 over t here, 1 over t there, 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 and so on. And so on. Straight lines. And here. So what we have is all Fourier series coefficients are 1 over t, where t is the time period of that impulse train. So I can write this as a sub k equals 1 over t for all k. And suppose we switch the things around. Say I'm trying to write x of t with the approximation. How can I write this as an approximation? I can write this as k equals negative infinity to infinity a sub k e to the j k omega naught t, and x of t, which is simply the summation of impulses t minus nt, where n goes from negative infinity to infinity. That's what we have x of t here. And a sub k is going to be what? 1 over t. Fourier series coefficients of an impulse train are 1 over t, where t is the time period of the impulse train. Questions about this? Questions about the Fourier series coefficients of impulse train? This is going to be extremely useful when we start talking about sampling. So when you sample a signal, you essentially multiply the signal with an impulse train. So knowing the Fourier series coefficients and later on the Fourier transform of impulse will be very helpful. So this is the first step in that conversation. All right, let's keep moving here. Now we are talking about the fundamental period of sum of periodic signals. So let's say we have a fundamental period t sub 0 of a periodic signal x of t, where x of t is the sum of two periodic signals x1 and x2. x1 has a time period of t1 and x2 has a time period of t2. So if I want to find out the fundamental period t sub 0 of x of t, then t sub 0 is simply the least common multiplier between t1 and t2, of which those are the time periods of x1 and x2 respectively. So I need to find the LCM of t1 and t2, and that will give me the time period of the sum of those periodic signals. And if you look at it in terms of fundamental frequency, which is the reciprocal of time period, you simply say f0 is going to be 1 over t sub 0, which is the fundamental period of x of t. This is going to be the greatest common divisor of t1 and t2. So if you can find greatest common divisor of t1 and t2, you get f0, the fundamental frequency of the resulting waveform. If you find the LCM of t1 and t2, you find the fundamental period of the resulting waveform. And you can extend that to t1, t2, t3, and finite number of periodic signals. Now let's do a quick example over here just to get a better sense of things. So we have two periodic signals over here. Clearly they are periodic because one is a sine, the other is a cosine, and they have different time periods. So our first goal will be to find out their individual time periods and fundamental frequency, but it is easier to find out the fundamental radian frequency first. So the fundamental radian frequency for the first one is 2 pi divided by 5, and the fundamental radian frequency for the second guy is going to be omega 2, is what? Pi divided by 5. No, that's frequency. This is going to be 4 pi divided by 5, 2 pi divided by 5. Okay. Sine omega t, which is sine 2 pi ft. So kind of mix them both here. F1, what is F1? F1 is going to be divided by 2. So 2 divided by 5. F2 is going to be 1 divided by 5. And quickly we can write T1 as 5 divided by 2, and T2 is 5 divided by 1, so simply 5. All right, so I found out the fundamental, sorry, not the fundamental, time periods of those individual periodic signals, T1 and T2. Now, if I want to find out the time period of the sum, T sub 0, which is the fundamental period of x of t, the sum, this is simply going to be the LCM, least common multiplier of 5 over 2 comma 5. So over here I can pull out a half from both of them. I have got LCM of 5 comma 10. Lowest common multiple of 5 and 10 is going to be 10. This evaluates to a 5. So that would be answer. That's the fundamental period. And if we know that, we also know that F0, which is 1 over T0, should be 1 over 5. Whatever units, so seconds and hertz. All right, so that was a quick example. Now there's a question about going back one. So I'm going to go back one slide and hold for a few seconds. In the meanwhile, Alan, I think I answered your question So if you have 3 signals, 5 signals, 10 signals, you keep going. You have to find the least common multiple between all of them, and that would give you the fundamental period of the overall signal. And if no such fundamental period exists, that means that the overall resulting signal is not periodic. All right. I hope you were able to take uh, down the notes here. Tommy, is it okay if we move forward? All right. So we did an example here for with two periodic signals. One is sine, one is cosine. We found out the fundamental period of the overall signal. Let's get into the properties of the Fourier series. Now this is the first property, which is the linearity property. So let's start with x of t. The Fourier series coefficients of x of t are, suppose, a sub k. So ak are the Fourier series coefficients of x of t. Then if you scale x of t, where alpha is a scalar, if you scale x of t by alpha, then the Fourier series coefficients get scaled by the same alpha. And it's very easy to prove, because all you have to do is use the formula for Fourier series coefficients, which involves an integral. And you say, okay, my new signal is alpha x of t. Because alpha is a scalar, it'll come out of the integral, and you will end up with alpha a sub k. It's pretty straightforward to prove this, because integration is not going to be dependent on alpha, so it can come out of that integration. Alpha x of t, Fourier series coefficients, alpha a sub k. This applies for any scalar alpha. Now next, we consider two signals. X of t, the Fourier series coefficients are a sub k. Y of t, another periodic signal, the Fourier series coefficients are b sub k. Then if you add x and y, x of t plus y of t, the Fourier series coefficients of the sum of those signals will be a sub k plus b sub k. Again, by using the definition of Fourier series coefficients, the equation that involves an integral, you can prove this very quickly. Now to combine the two statements here, if x of t, the Fourier series coefficients are a sub k, and for y of t, the Fourier series coefficients are b sub k, then a x of t plus b y of t, scaled version of x of t plus scaled version of y of t, will have the Fourier series coefficients a sub k plus b sub k. A and b are scalars. So this is combining the the homogeneity and the additivity properties. You get the linearity. So the last one is what is the crucial one. That's the linearity property. The first and the second one are homogeneity and additivity respectively. Let us use that simple linearity property to find the Fourier series coefficients of this particular periodic waveform. So we are given x of t, and I'm assuming that m1 and m2 are scalars. So those are the heights of those waveforms. And the time period of the signal x of t is cap t. And in fact, the way it is sketched, the time period of the shorter rectangle is also cap t, and the time period of the taller rectangle is also cap t. and everything is centered around 0. So it's in a very convenient form for me to use linearity. But apart from linearity, I would have to use a reference result, and the reference result that I'm referring to is this there. So I'm going to do this. I'm going to copy paste this guy here so that I have a quick. This is the Fourier series coefficients of the pulse train. That's my reference result. So I'll start with writing x of t as the sum of two pulse trains. So I'll say x of t, let's say I write it here. X of t is pulse train t1 comma t. This is the one that has a height of m1. So in fact this is not that, this is m1 times that, plus I have m2 times pulse train over here. This guy is going to be t2 comma t1. Oh, sorry, not t1, just t. I made an error over here. What is that error? Yes, this needs to be m2 minus m1. All right, so I have the reference result, and I hope that you can see this is going to be extremely useful here. So what would be the Fourier series coefficients of x of t? Say x of t Fourier series coefficients, let me call this a sub k, and a sub k, because I know the reference result, now is going to be m1 multiplied with 2t1 divided by t from the reference result, sinc k omega naught. What is omega naught? All right, I need to do this. Omega naught. Capital T is t, so time period is t, which means fundamental is going to be 1 over t, and omega naught is going to be 2 pi divided by t. All right, so k times 2 pi divided by t times t1, that's a sub k. From the first piece, so let me color code this. Let's say we have blue here, so I will use blue for this guy and blue for this guy. Then I have the second one, m2 minus m1 times 2 t2 divided by t, sinc k omega naught is the same, 2 pi divided by t times t2. And let me color code that, maybe yellow. Now, I hope you see that a really bad way to solve this problem is by applying the definition of Fourier series coefficients to the overall signal. Then you will be spending a lot of time to get the same result, right? So that's not a very good use of your Fourier series definition, the one that involves an integration over the time period while you are projecting that signal onto an orthogonal set of complex exponentials. So what I'm trying to say is, if you know certain reference results, you can take advantage of those reference results along with the properties of Fourier series to solve a lot of these problems. All right. Before I move on and write for all k over here, which I cannot write that just now, I am going to check whether A0 satisfies this or not. What is A sub 0? Which is the DC value. The DC value is going to be simply the area of x of t over one time period, right? So I'm going to highlight this over here like this, right there, and then divide it by the time period t. Integrate over one time period divided by the time period, you get the DC value. What is that going to be? Well, if you calculate that out, for the blue rectangle, you have m1 multiplied by 2t1, that's the blue rectangle, plus m2 minus m1 multiplied by 2t2, that's for the yellow rectangle, that's the area. You're adding them up and then you divide it by time period t. And as you can see, this form satisfies A sub k. So I'm going to quickly say this satisfies the earlier result. So I can say for all k for the earlier result. What I mean by satisfies earlier result is if you substituted k equals 0 in the previous equation, you would get A sub 0. So now I can say this is for all k. That's Fourier series coefficients of two pulse trains that were added together of different heights and different individual time periods. All right, so I hope you found that example helpful. Let's move on to the second property of Fourier series, vertical shift property. And we have kind of looked at this informally earlier on as well before the break, which essentially means that if I move the signal up and down, have a vertical shift, I'm just playing with the DC value of the signal. I'm not doing anything else to the first harmonic, second harmonic. I'm not changing A1, A2, A3, A minus 1, A minus 2, A minus 3. I am simply changing A sub 0. So let us try to state that formally here and also prove it. So suppose that you have x of t whose Fourier series coefficients are A sub k. Then if you add a constant c to x of t, what are going to be the new Fourier series coefficients? We are calling it b sub k. So the property says that b sub k is going to equal A sub k when k is not equal to 0. And when k is equal to 0, b sub 0 will equal A sub 0 plus c. So only the DC Fourier series coefficient, the DC value changes. Everything else will remain as is. Ryan says this method works for only pulse trains. Actually, it works for every signal that has a standard form like this. So there will be later on, so far how many forms do I have in terms of standard forms? I have the pulse train and I also have the impulse train, right? So far, the two standard Fourier series results that I have are the Fourier series coefficients of pulse train and impulse train. I could add more. I could add the Fourier series coefficients of triangular waveforms to this, and I can use that as well. So it really depends on how many standard reference results do you have at your disposal. But linearity is a consequence of the Fourier series definition. So linearity can apply everywhere. It's not limited to pulse trains. All right, let's move on here. Okay, so we are talking about the proof of the vertical shift property. So A sub k, what is A sub k? A sub k are the Fourier series coefficients of x of t. How can I write that in this way? To find A sub k, I would need to consider 1 over t integral 0 to t. Why do I need to do 0 to t? Because I can, right? I can do negative t over 2 to t over 2, but I also can do 0 to t. So in this case, I'm considering 0 to t. X of t e to the minus jk omega naught t dt. So that's the definition of finding the Fourier series coefficients for a given periodic signal x of t. Now, when you have a new signal which is x of t plus c, the Fourier series coefficients of that signal were defined as b sub k. So bk can be written as 1 over t, right? The time period of that signal is not going to change if I move the DC component. If I move it up and down, the time period doesn't change. 0 to t, x of t plus c, the new signal, times e to the j k omega naught t. Omega naught t doesn't change because t doesn't change. Now this can be broken up into two pieces. Using the linearity property of integration, I can break it up into two pieces. One has x of t and the other has c. X of t, the first piece will give me a sub k. The second piece will give me c over t multiplied by t. So that will simply evaluate to c when k is 0 and will be 0 when k is not equal to 0. See, I just forget when. Hold on. Which second term? This second term will go to 0 only when k is not equal to 0. When k equals 0, so when you integrate e to the negative jk omega naught t dt, what do you get? You get e to the negative jk omega naught t divided by negative jk omega naught. And you are integrating that from 0 to t. So that function that you evaluate after you substitute the limits will go to 0 only when k is not equal to 0. When k equals 0, it will go to c. You can check these two. So it's not equal to 0 all the time. It's equal to 0 only when k is not equal to 0. When k equals 0, so let's do this. All right, for the integration, what do you have? Let me do this in blue. For the integration, you have c over t, then you have e to the negative j k omega naught t divided by negative j k omega naught, and you are integrating that from t to 0. And this will result in c over t e to the negative negative j k omega naught divided by, so here omega naught is 2 pi divided by t, okay, 2 pi divided by t multiplied by t divided by negative j k omega naught plus c over t times 1 over j k omega naught. And this guy will cancel out here. You get e to the negative jk times 2 pi, and you can use your Euler's identities to simplify that. All right. So you will go back to that same result here. Let me erase this out now that you guys know how to do this. So combining these, you can say that bk is going to be ak plus c when k is 0, and when k is not equal to 0, the new coefficients will be the same as the old coefficients. So when you do a vertical shift, you only impact the DC value. You only impact a sub 0. Example. What do I have over here? The top function x of t is a standard result. Very nice. What is that standard result for? X of t, I can write x of t as, let's see, x of t can be written as 1 divided by 4, because the height is 1 over 4, multiplied by pulse train. What do I need to use for t1 and t? T1 is going to be 1, because this is 1, and capital T is going to be 4, because this is 4. So for that particular pulse train, I know the standard result. So let's quickly do it. Let's fill up these things here. T1 is, what did we say? 1. T is 4. What is omega naught? Omega naught is 2 pi divided by T, which is 2 pi divided by 4. So pi over 2. What is A sub 0? A sub 0 is area. So all this, guys, the area under this divided by the time period. What is the area under that? 2 times 1 over 4, right? And divided by T. What is T? 4. So let's do 1 over 8. So what is AK? AK is going to be, for the standard result, I have this. 1 over 4, 2t1 divided by t, sinc k omega naught t1. So I can use whatever I have found so far and substitute it in my standard result. So let's see. I get 1 over 4, 2t1 divided by t, sinc k omega naught t1. So you simplify this, what do you get? You have 1 over 8 and sinc k pi over 2. Just to quickly check, does A sub 0 fall in this? A sub 0 was 1 over 8. So when you put k as 0 here, you get sinc 0. Sinc 0 is 1, so 1 over 8. So it satisfies. Beautiful. So for all k, I can write this. 1 over 8 sinc k pi over 2. So that's A sub k. Now, y of t is a vertically shifted version of x of t. And it is not a straightforward shift. It is shifted down by 1 over 8, but it is also scaled by 4, because the height over here is half and negative half. So if you just move this down by 1/8, you will get plus 1/8 minus 1/8. So you would have to multiply the signal after you shift it down by 4 so that you can get plus half and minus half. So what would be the Fourier series coefficients of this signal? Well, let's try to, in order to do this a little bit better, let's do this. I have A sub k as 1 over 8 when k was equal to 0, and I had 1 over 8 sinc k pi over 2 when k was not equal to 0. And I'm writing this separately as cases k equals 0 and k not equal to 0 because there is a vertical shift involved and only the A sub k will get impacted because of that. All right, so when you do the vertical shift, what would be the vertical shift down? In order for that center to be centered around 0, you would have to shift it down by 1 over 8, right? 1 over 8, and that guy is 1 over 8. So when you go down, you're subtracting, which means for y of t, if you have two results, the first result is going to be 0 when k is equal to 0 because you have moved it down by 1 over 8. Next, when k is not equal to 0, the Fourier series coefficients are going to be the same, except there is a multiplication of 4 that is involved to take care of the 1/2 and 1/2, negative 1/2. So that means my Fourier series coefficients, and linearity applies here. I'm going to have to multiply this guy with 4, which means I get 1/2 sinc k pi over 2. And this is going to be for k not equal to 0. So I hope you see how you can apply the vertical shift, and we have also applied linearity over here to get the Fourier series coefficients of y of t, which is a periodic rectangular pulse train, but it is centered around 0. Now, a few things that you should quickly check. Because it is centered around 0, the average value should be 0. So the DC value should be 0, which should check out. So, there are ways to kind of quickly check whether you are on the right track or not. I think that this is a result that we might have looked at earlier. I think half sinc k pi over 2 is something that we proved for the pulse train earlier. All right, so that's another example, and I hope you find that helpful. Next, what happens when you shift things horizontally? When you shift things horizontally, say if you start with x of t, and the Fourier series coefficients of x of t are a sub k, then if you shift x of t by t sub 0, maybe you are advancing the signal, maybe you are delaying the signal, but I'm referring to the resulting Fourier series coefficients as b sub k. B sub k will be related to a sub k by using this equation. B sub k is going to equal a sub k multiplied by e to the plus and minus, depending on plus and minus here, j k omega naught t naught. T naught is t naught here. Omega naught is the fundamental radian frequency of x of t. So if you shift it, omega naught doesn't change. But because you're shifting it, the amount of shift will matter. K is the index, AK are the old coefficients here. So AK are the old coefficients, K is the index, omega naught is 2 pi divided by T, the fundamental radian frequency, T0 is the time shift value. Could go either way, could be a delay, could be an advance. B sub K are the new coefficients of the shifted, horizontally shifted signal. X of T plus and minus T naught. Now, I think I look at this later on, but let me ask you this. By looking at this red box here and the relationship between B sub K and A sub K, can you state two things? The first is the magnitude relationship between B sub K and A sub K. Can I say that the magnitude of BK and A sub K are the same? The magnitude doesn't change when you do a horizontal shift. That is a true statement, because the only thing that changes is the phase, because I'm only multiplying by the phase. And if you find the magnitude of e to the plus and minus j whatever, that is going to equal 1. So magnitude doesn't change, but there is a phase change. Phase change that depends on the time that you shifted your signal by. All right, let's quickly prove this time shifting property. Start with what we know. We know that x of t has the Fourier series coefficients a sub k. So a sub k can be written as 1 over t integration from 0 to t x of t e to the minus j k omega naught t dt. The Fourier series coefficients of the shifted signal can be written as b sub k equals 1 over t 0 to t x of t plus or minus t sub 0 e to the minus j k omega naught t dt. Now, if this is b sub k, I'm going to consider the case that x of t minus t0 for the remaining of the steps. You could have gone with t plus t0 as well, and you will get the same result. Just to keep things simple, I'm considering only the minus here. So if you do that, b sub k is this 1 over t 0 to t x of t minus t0 e to the minus jk omega naught t dt. Quick change of variable. I want this to be one entity, so I'll define that as v, t minus t0. dv is the same as dt. The lower limit of the integration was 0. Now it becomes negative t0 with respect to v. The upper limit was capital T. With respect to v, it will become t minus t0. Substitute these things in the integral. You will end up with bk equals 1 over t. The lower limit has changed from 0 to negative t sub 0. The upper limit has changed from capital T to t minus t0. You have x of v, and then you also have e to the minus jk omega naught v plus t0 dv. So it's a simple change of variable that you have applied. And next we note that e to the negative jk omega naught t naught are independent of v, so I can pull that out of the integral. So outside the integral I have 1 over t e to the minus jk omega naught t naught, and inside the integral I have everything that has a v in it, x of v e to the minus jk omega naught v. So that red box is a sub k. The only difference is we are going over one time period, right? Minus t0 to t minus t0, that's one time period. X of v e to the minus jk omega naught v dv. So that's a sub k and multiplied by e to the minus jk omega naught t naught. That gives us the result that we were after. So if you had gone with plus, you would have gotten plus here with the same proof. All right, so I hope that this proof was helpful. Let's see. I want to next formally talk about the relationship between b sub k and a sub k, specifically in terms of their magnitude and phase. So note, bk equals a sub k multiplied by e to the plus or minus jk omega naught t naught. That was what we had for the time shifting property. Now what about the magnitude? So if I find the magnitude of b sub k, I get magnitude of a sub k. Well, let me write it together first. Plus or minus jk omega naught t naught, which is going to be magnitude of a sub k multiplied by the magnitude of e to the plus and minus jk omega naught t naught. And we know from Euler's identity that this is simply going to be cosine plus and minus j sine, right? Inside the parentheses you have k omega naught t naught, right? So if you want to continue with the magnitude, what do you have? You have magnitude of a sub k multiplied by the magnitude of the complex number. So you will do cosine squared plus sine squared, which will come down to a sub k, right? So I hope you see that doing a time shift or a horizontal shift doesn't impact the magnitude of the Fourier series coefficients. So let's write that summarizing statement here. Time shift or horizontal shift operation doesn't change magnitude of Fourier series coefficients. Now, Next obvious question. How about phase? It does change. How does it change? The phase of B sub k is going to equal the phase of A sub k plus or minus j k omega naught t naught. Oh, sorry, not j, just k. So we are only changing the phase by plus and minus k omega naught t naught. So the phase does change, the magnitude doesn't change. All right, let's move on. Questions so far? With the horizontal shift, vertical shift, and the linearity properties. All right, another example. I have x of t, whose Fourier series coefficients are given to me as a sub k, and I need to find out what a sub k are. Like I need to find out. So that's the question. So I'm going to start off with what we know. We know a standard result. What is that standard result? The standard result over here is, consider a new signal y of t, which is centered around 0 and that has a time period of 4, but it is on for 2 seconds. Why did I choose y of t in this way? I wanted to choose it this way so that it is on for 2 seconds and the time period is 4. That matches up. That is why I'm considering this pulse train to have those numbers for t1 and t. And if I use those numbers, I get b sub k, the Fourier series coefficients of this guy, as half sinc k pi over 2. That is for all k. Do you agree with this? Let us quickly verify. Observe y of t over here. Y of t over here is half and negative half. So the amplitude, peak to peak amplitude is 1. And the t1s and t's are all matching up. So if I push this up by half, what do I get? Half here, and this guy will be half sinc k pi over 2, which means the overall thing is just half sinc k pi over 2. So that way I can quickly validate that this is actually correct. And it also satisfies our standard results of 2t1 divided by t sinc k omega naught t1. It satisfies that. So you can find out omega naught, plug it in that standard result, use t1 as 1, right? t1 is 1 here and capital T is 4 here. That is also already written. So you can plug that in and find bk. So how is x of t and y of t related to each other? Notice we are after a sub k. We know bk from the standard result. So x of t is related to y of t as delay the signal by 1 time unit, which means move it right by 1 time unit because I need to line it up by 0, and also scale it by 2 because the amplitude over here is 2. So what should I do in terms of the Fourier series coefficients b sub k? Well, I can say b sub k, the Fourier series coefficients of y of t, x of t, oh no, not x of t, a sub k. A sub k is going to equal, for the amplitude scaling, I have 2. For the time shift, I have b sub k multiplied by e to the minus j k I need omega naught is pi over 2, and I also need t naught is 1. Let me highlight this, 1 because that is 1, 2 because that is 2, and well, bk because that is y. Next, simplify. What do I have? 2 times, let's see, e to the minus jk pi over 2. That's in a nice form, so I can just put that as negative j raised to k, and then 2 multiplied by half sinc will become sinc k pi over 2. This is for k not equal to 0. And for k equals 0, let me just find that out. A sub 0 is going to be area divided by t. What is the area? 2 times 1 divided by, oh sorry, no, not 2 times 1. That's for y of t. For x of t, it is 2 times 2, 4 divided by t. T is also 4, so 1. That is for k equals 0. So that will be my result. My result, I can write it over here. A sub k is going to equal 1. Oh, which is actually included in this. Negative j raised to k sinc k pi over 2 for all k. Because when k is 0, this satisfies. So it is included. So that's the result. Sinc 0 is 1. All right, let's move on. The next property that we are going to look at is the time flipping property. So what happens to the signal if you flip it about the vertical axis? X of t, the Fourier series coefficients of are a sub k. The flipped version of x of t, which is x of minus t, the Fourier series coefficients of that are, say, b sub k. Then bk are going to equal a sub minus k. So the Fourier series coefficients will also get flipped about the vertical axis. So let's try to prove this. A sub k, Fourier series coefficients are x of t, 1 over t, 0 to t, x of t, e to the minus jk omega naught t dt. Alright, we know that from the definition. And I'm considering a time period of 0 to t here. I could have also done negative t over 2 to t over 2 or several other combinations, but I'm choosing to do 0 to t because the math is a little bit simpler to handle this way. bk is the bk are the Fourier series coefficients of the flipped signal. So 1 over t, 0 to t, x of minus t, e to the negative jk omega naught t dt. Right? Then do a change of variable because I need to get rid of a negative sign here so that I can write it in the usual form. So I'll use v as negative t. So I get dv as negative t dt. My lower limit will remain unchanged. My upper limit will flip to minus t. So bk will, because of this minus sign, I have a minus sign there, and I continue to have 1 over t. My integration limits I talked about, x of v e to the jk omega naught v dv, because negative t is v. Simplify, what do you get? 1 over t. Now integration is scanning from negative t to 0, so the negative side got eliminated. X of v e to the jk omega naught v dv. Now, since the the signal x of t is t periodic with time period t, what we can do is we can say whatever you do from negative t to 0, you can also do from 0 to t. So I'll say 1 over t integration 0 to t x of v e to the jk omega naught v dv. That is simply a sub minus k, because the only difference over here is the addition of that minus sign, right? So that's just a sub minus k. That's how we prove that the Fourier series coefficients will be also flipped. So b1 will equal a minus 1, b negative 1 will be a1, and so on. You can apply all that. Okay, next let us go into a very very useful property here. This tends to be like extremely useful, because you will see a lot of derivative property being used, because here is the thing, here is the reason. What are your standard results? The standard results are for pulse train and impulse train. So if you want to find out the Fourier series coefficients of quadratic, cubic to the power of 4 periodic functions, you can differentiate those signals once, twice, 3 times, more, as many number of times as you want, get down to a pulse train or even an impulse train. You know the Fourier series coefficients for that, so use them, and then you go back by using the time derivative property. So this can be really really helpful to do many signals. So let us take a look at what the time derivative property is and also its proof, and then we'll look at an example. So you have standard way to start, right? X of t, the Fourier series coefficients of x of t are a sub k. Then when you differentiate the signal in the time domain, d over dt for x of t, time derivative of x of t, then for the Fourier series coefficients, they are going to be multiplied by j k omega naught. So ak remains as is. When you differentiate the signal, then the resulting signal will simply have the Fourier series coefficients being multiplied by j k omega naught. As simple as that. So let's see if this works. Proof. Ak are the Fourier series coefficients of x of t. So ak equals 1 over t integration from 0 to t x of t e to the minus j k omega naught t dt. Alright. Next, b sub k, the Fourier series coefficients of the derivative of x of t. 1 over t integration 0 to t d over dt of x of t. Derivative of x of t e to the minus j k omega naught t dt remains as is for the formula of finding the Fourier series coefficients. Next, I'm going to use the product rule of integration. Integral u dv over dx is uv minus integration v du over dx multiplied by dx. It's in a very nice form, in a convenient form, so I can apply that straight away. What do I get? I get all of this. 1 over t x of t e to the negative j k omega naught t with limits 0 to cap t plus j k omega naught integral 0 to t x of t e to the minus j k omega naught t dt. Notice what is this. Let me do it in blue because it is that. That is my a sub k. This is my j k omega naught. And it turns out that because x of t multiplied by e to the negative j k omega naught t with the limits cap t and 0, both those substitutions are the same. So when you substitute the limits, since it is t periodic, they will cancel out and you get a 0 there. So you get b sub k as j k omega naught. 1 over t comes in from here, and that was color coded to be yellow, I believe, and that was color coded to be blue, which is simply going to be jk omega naught multiplied by a sub k. So multiply the Fourier series coefficients by jk omega naught and you're done, where omega naught is the fundamental radian frequency of x of t. So even if you differentiate it, the fundamental radian frequency doesn't change. All right, let's try to do an example here. Instead of rectangles, now we have a triangle. So x of t is a triangle waveform, it's periodic, whose Fourier series coefficients are a sub k. So these are the Fourier series coefficients, and I'm trying to find out a sub k. That's the problem. So let us do some quick things over here. What is the time period? Time period is 4, which implies that omega naught is going to be pi over 2. Okay, that's helpful. It's a triangle. So when I differentiate x of t, what do I have? I get something like this. And when I have a pulse train, I can use all the pulse train based results, 2t1 divided by t, sinc k omega naught t1, all those standard results for the derivative of x of t. And once I find those, I can use the time derivative property to go back and find a sub k. So let's do that. The derivative of x of t, which is the derivative of this, is going to be that. Do I agree with this? Let us see. From negative 2 to 0, slope going up. What is the slope? Plus half. Plus half there. Going down with a slope of negative half, and so on. It's periodic. So the derivative of x of t, which is, I'm writing that as y of t here, has the Fourier series coefficients of called b sub k. And b sub k, we know from the property, are simply going to be j k omega naught times ak. What is that? J k omega naught was pi over 2 and a sub k. Okay. So far so good. Now I need to find out bk. I think I did it earlier as well, but I'm just going to write that over here. Obtain bk, b sub k, using the vertical and horizontal properties along with the result of the general pulse train. So we have done this before, right? We have done that kind of thing before, where you take a general pulse train and move it down or up, move it left and right with the horizontal shifts to find bk, right? Once we find bk, we can find ak by just dividing the Fourier series coefficients bk by jk omega naught. So obtain bk using vertical Fourier along with the result, and then we do this. Note, we also have to find the DC value of x of t separately. So in this example, what is going to be a sub 0? A sub 0 in this example is going to be area divided by t. What is the area? I've got the area here. Half base height 2. Time period is 4. So 2 divided by 4, half. Right. So a sub 0, we know that already. How to find b sub 0? Well, find b sub, let's try to do this. Did we do this already? Half like that. Let us see. I think we did something like that earlier on. So we may have the result already. Oh, we had this. So this was 0 for k equals 0 and half sinc k pi over 2 for for that, but this also has a horizontal shift. So the horizontal shift is, let's see, the horizontal shift is -1. Okay, so I think I can do this. So I will copy this guy from here. The height is the same. Right here. So bk equals that. uh, I need to adjust a few things. What is that? This is going to be multiplied by e to the minus j k omega naught t naught multiplied by e minus j k omega naught, what is pi over 2 t naught. And I hope you see that I need to multiply this by so if I move it right, let's just see. I actually need to move this left by 1 time unit. If I move it right, then I start off positive, which I don't have here. Right, I have negative. So this needs to be plus and plus. So I'm advancing the signal by 1 time unit. That's going to be my bk. So this is when k equals 0 and k doesn't equal 0. So what is that? Is simply 0 here, and for the e to the j k pi over 2, it is simply j raised to k, and half remains as is, and you have sinc k pi over 2 when k is not equal to 0, and this is when k equals 0. So that's going to be your bk. Once you have bk, how do you find ak? You take bk and divide it by jk omega naught. Jk pi over 2. So 0 remains 0. Let's see. For 0, what are you going to have? You're going to have 0. Right. But for 0, I need to bring in half here, because that's what I found here. But for other than 0, I'm going to have j raised to k, but I also have a j in the denominator, so I'm going to have j raised to k minus 1. I have half. I have sinc k pi over 2. I also have a divide by k. All that is going to be for k not equal to 0. All right, so I hope that gives you a good idea about how to go about using the time derivative property and the standard results to find the Fourier series coefficients of a triangle waveform like this. Or you could extend it, right? You could say, okay, I have parabolas, so differentiate it once, differentiate it twice, and then you go back by dividing it by jk omega naught twice, and that's how you would tackle that. So we'll take a look at more examples when we come back on Thursday. That's all I had planned for you guys today.